the situation for number 7 is similar to the situation for number 6, except now we have radius R1 and radius R2. Let's make that look a little more like an R. Okay? Instead of the cross-sectional areas A1 and A2, we just have the radii R1 and R2. Now we're going to use the results that we got in problem 6 to say that the velocity V2 over V1 equals A1 over A2 from the continuity equation. We're going to assume that we know that. And then we want to find out what A1 and A2 are. Well, radius R1 means that the area is pi R1 squared. Radius R2 means we have pi R2 squared. So those are our two areas. So that the ratio A1 over A2 is the ratio pi R1 squared over pi R2 squared. The pi's divide away, and we have R1 squared over R2 squared, which of course is the same as the quantity R1 over R2 squared. So we conclude that the ratio of the velocities is the squared ratio of the reciprocal, well, the reciprocal squared ratio of the radii. Just like the ratio of the velocities is the reciprocal ratio of the areas, it's also the reciprocal ratio of the squared radii, because it's a squared radius that we use to find the area. Now in this problem we're given V1, R1, and R2, and our strategy is very similar to what we did before. From R1 and R2 we find the ratio A1 over A2, which is just your R1 over R2 squared. That's your A1 over A2 you see from up here. And then from A1 over A2 we multiply that by V1 to get V2. So A1 over A2 and V1 give us V2. And now that we know both V1 and V2, we can find our change in 1/2 rho V squared. And the negative of that change, again, is our pressure change, since we're at a constant height.